Hi everybody. Today we're going to have a little bit of a different video. It's going to have a different feel as we go through some stuff today. What I want you to do is we're going to address sine law, something called an ambiguous case. Today is going to feel different because it's not going to really address new stuff. So I want you to kind of get that idea like we're talking about a new topic today. Really what we're going to do is we're going to add some depth to the old stuff that we started addressing last year in dealing with sine law. We're going to actually start to talk about how we create diagrams and how we draw triangles. So for today, kind of sit back a little bit. We're going to draw some triangles, and then we're going to address a little bit of trigonometry, and we're going to talk a little bit about a calculator issue as we progress. So it's going to have a different feel. Follow along today. We should be good. So, what you see on the screen today is going to be what we're going to talk about over the course of the day. And we're going to use kind of this context to discuss a couple issues, some assumptions that we've been making as we've been working through dealing with some of our trigonometry. So, I want you to notice that what we're going to do for a number of problems is actually draw sketches of triangles. We're going to kind of set the trigonometry aside, but we're going to use it as a tool to discuss certain other situations that arise. You'll notice that in each of those problems, we start to address different information we've been given about a triangle. So, in those first two, we're talking about being given all three sides. In our next problem, we're going to address being given three angles. And then we start to work our way through kind of a combination of those. So, what if we have two angles and one side? And then on the last ones, what if we've been given one angle and two sides? And so we want to address all the different situations that can arise if you've been asked to examine a triangle without being given the diagram and only being given properties. So let's jump in and see some situations that could occur. Now, okay, so when you take a look at that first question, we're going to go through a series of problems that are going to ask you to draw a sketch of a triangle given certain properties. And so you'll take a look at both A and B, and I want you to draw a quick sketch of a triangle with side lengths 3, 7, and 11. And I'd like you to go through and draw a diagram of 3, 4, and 6. Go ahead. Now, the first thing I'd like you to notice is when you drew those diagrams, did you simply say 3, 7, 11, 3, 4, 6, and basically draw what looks like a similar triangle in both cases, but labeled different? I actually want you to examine your diagrams really closely and just see, does the side 11 look longer than the side 7? Do the sides 3 look like the shortest sides on both triangles? And maybe more importantly, does it look like you basically drew equilateral triangles but labeled them differently? Or does it look like you drew isosceles triangles and labeled them differently? What I want to get to at the very beginning here is the idea of us constructing more realistic diagrams. And so we're going to take our time a little bit to be able to draw those diagrams, and we can see some issues that can arise. So I want to play along with what I imagine most people did on the first one. That they drew a triangle that had a side length of 3, 7, and 11. Now, we should be good that to go through, and if we were asked to actually solve that triangle, we would have to go through and find the smallest angle first, or we would prefer to. And so in that triangle, if I label it as triangle ABC, I would be finding angle C first. And so I noticed that I have side, 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 and I could work my way through using cosine law. That side C squared is going to equal side A squared plus side B squared minus 2 times 7 times 11. So 2 times 77 is 154 cos of C. And we could then, and maybe jump a step, that's going to give us 170. So when I subtract that, I'm going to have a negative 161 divided by negative 154 is equal to cos C. And maybe if I just wrote that in good form, I could at least get rid of my negative divided by a negative. Okay. What I would like you to do now is to use your calculator and find the angle measurement of C. You should be noticing a major problem on your calculator. And so when we see that error message pop up on our calculator, that's got to tell us that there's a problem with what we're trying to calculate. And I'd like you to notice that right within your problem, you should be able to see why your calculator is telling you that that is not possible. When you take a look, cos talks about my adjacent side divided by my hypotenuse. And so if I was to construct a right triangle, I'm trying to tell my calculator that my adjacent side has a length of 161 and my hypotenuse has a length of 154. And we know that that can't be possible because my hypotenuse must be the longest side. And so your calculator spits out error to tell you that you've actually punched in something wrong. And so I want us to take a look back up at that information and notice that that triangle that I drew in red isn't possible. That's what the blue error is telling me. I'm going to draw a very, very quick 3 side lengths. That we have a side length that is 3 centimeters long. We have another side length that is 7 centimeters long, so a little bit longer than double that length. And then we have a side length that is 11 centimeters long. I want you to notice that for you to construct a triangle using those 3 yellow side lengths, you would have to bend those lengths in a way to get them to all connect. And if I was to then say, well, I'm going to put this 7 and this 3 and attach them there, then maybe I have my length of 3 that goes on this angle, and now my length of 7 that goes on... Well, my length of 3 and my length of 7 can't connect and then rotate to meet up with the side 11 at its endpoints. That there is one very, very quick property that maybe you've overlooked in the past. Let's leave that right now, and let's go ahead and let's deal with B, but we're going to remove all the trig. So I'm going to jump in right away and say I have a side length of 3 meters. And right away, I'm going to connect it with my side length of 4 meters, a little bit longer. Sorry, I labeled that as a centimeters. Right below it, I'm going to draw my length of 6. So it would be a little bit shorter than the combination of the other two. I'm hoping that we can see that since 3 plus 4 is greater than 6, that the sum of the 2 shorter sides is longer than the third, that you would be able to rotate or bend them at that vertex and enable you to construct your triangle. If we look back at the yellow line segments at the bottom of problem A, you'll notice that 3 plus 7 is not greater. It's less than the longest side. And because of that property, we could never put together a side 3, a side 7, and a side 11 to form the triangle. If we tried to, it would look something like this. 3 would be short, 7 would have to rotate some distance, But if I was to then say, there's my big long side 11, I would not be able to connect that side 7. The 3 and 7 are too short to meet up with the 11 at its endpoints. That may be a property of triangles that you were unfamiliar with. But maybe that just gives us a little bit of background that when I first asked you to sketch those triangles with those side lengths, we just generically drew down 2 triangles. We labeled them with the given dimensions without any real thought as to how do I put together those properties to create my triangle. So what we want to look at for the rest of the day today is how do we construct diagrams when given properties of triangles. Okay, so what we see now in problem C is I've given you the 3 properties of 40 degrees, 60 degrees, and 80 degrees, and I want you to draw a triangle. So what we're going to always do when we go to construct our triangle is we'll start to build it with the properties. So I have this 40-degree angle, and if I go to draw my angles, I always think of a square. Because I know that the diagonal of a square creates angles of 45 degrees. And so when I go to draw my triangles, I always kind of use my 45 degree as an idea. And so when I go to construct a 40-degree angle, I know I've got to be a little bit flatter than my perfect 45. So to remove that little sketch, what I'm now going to do is I'm going to construct my angle of 40 degrees. And so I have this 40-degree angle that's going to have a bottom side and something a little bit flatter than a perfect 45. Maybe there's my angle of 40. And I know that that angle of 40 will have one ray that has a certain length to it and another ray that has a certain length to it. I just don't have any requirement on what those lengths are. Okay, I've also been given an angle of 60. And so maybe I have this angle of 60 that has a bottom side and a side that's a little bit bigger than my perfect 45. And each of those rays could have a certain length. Now I have a third angle that is 80 degrees. And the first thing I'm going to do now is say, well, is it possible to construct a triangle with 3 angles of 40, 60, and 80? We should come back pretty quick with an answer of yes to that, because you know that all 3 angles inside of a triangle must add to 180. So I do now have this 80-degree angle that I could go through and put into my triangle. Well, from the looks of it on my screen, my 80-degree angle would have to be up here somewhere, and a relatively big angle with rays that go out in every direction. I'm hoping that we can see just from that very crude diagram that it is possible if I have a very small 40-degree angle, a 40-degree angle with very small rays, and a 60-degree angle with very small rays, and a 80-degree angle with very small rays to construct a triangle. But I could also construct that triangle with bigger rays. My 60 may then look something like this, and my 80 may look something like this. And we may start to see that for you to go through and construct diagrams given a 40, 60, and 80 degrees, you could have multiple triangles. In fact, in this case, you have infinitely many diagrams that you could draw. There are infinitely many triangles then. That by being given 3 angles, there is no restriction as to what those side lengths could be. Now we know that they would all have to be proportional, given similar triangles, but there is an unlimited number of triangles that could be drawn. So very quickly, we've seen that in some cases, given the information, you can't construct a triangle. There are no triangles to be constructed. In other cases, one triangle was constructed. And now in problem C, infinitely many triangles could be constructed. So let's spend the rest of the day looking at, given information, what types of triangles could I create? So let's begin the exact same way. And if I was to give a recommendation as to how to draw decently accurate diagrams, I would always argue with you, draw your angles first. Angles are going to dictate some shape to some degree, and they're going to help you to construct more realistic diagrams. So as I take a look at that first, I've been given that angle A on a triangle is 40 degrees. So I'm going to start with angle A. If it's 40 degrees, then maybe that is my 40-degree angle. I've also been given an angle B, telling me that it's 60 degrees. So maybe over here somewhere, to the right, I have an angle that's at 60 degrees, a larger angle. Now, I know that in both of those cases, each ray could go on forever and ever and ever on both of those angles. Now, the way I've drawn that right now looks like it just formed a triangle. But I hope you see that I haven't formed a triangle yet, because I don't know the side lengths of any of those. So those angles could occur anywhere. Perhaps that 60-degree angle doesn't lie in that position. Perhaps it lies way out here, and therefore it would have constructed a different triangle. So just based on those two angles being given, I don't have enough to state how many triangles I have yet. But I haven't used that third property. And that third property is a side length. Now, if I take a look and I label all my information, I have angle A in red and angle B in blue. That would mean that this would have to represent side A, and this would have to represent side B. So the only location, given the way I've drawn my diagram, would have side C being located on the bottom. Well, since it gave me a side length and told me that the length of C is 12, then this side of 12 units long must take this location in the position of C. That actually tells me then how far apart angle A and angle B are, or the vertices of angle A and B. And so now that I know that this length at the bottom is 12 centimeters, given angle A, angle B, and side C, I only have one triangle that could be constructed. There's only one way to put together angle A, side C, and angle B. That would mean that these would all come together and form my triangle ABC. There's no possible way for me to be able to go through and deal or construct multiple triangles. And if we were asked to go through and then solve that triangle, I hope that we could see our kind of map, our pathway through being able to solve that triangle. We could very quickly, if I labeled this as C, find out what angle C was by taking 180 minus the sum of the other two. And then once you knew what angle C was, we could use sine law. Now that you know what angle C is, we could use sine law to find side B and side A. And so, one of the things that we want to take a look at then is in problem D, we were given two angles and one side. And hopefully then we can kind of see one key feature. That because we were given two angles, that really means we were given three angles. Because if we know two, then we know the third because of the sum of angles equaling 180. And since we knew what three angles were and one side, then there was only ever going to be one triangle that we could construct. Okay, now I want you to take a look at E. We've given you three properties. We've given you angle A, and side B. So unlike the last diagram where we gave you two angles and one side, we've now given you one angle and two sides. So let's go through and let's construct the diagram. So the first thing that I was given was angle A, which is a 30-degree angle. So that's going to be a pretty small angle. I was then given two sides. So I know that this 30-degree angle could go off, but one of the sides I was given was side A. And so side A being 13, I'm not quite sure where to put side A right now, because side A would have to be opposite angle A. So off on the side, I'm just going to draw that I have side A, and I know that it's 13 centimeters. I don't know how that side A should exist. What angle should it be on? Should it be on this angle? Should it be on this angle? Should it be really steep this, really flat? I'm not sure. I'm going to leave that there for a second. I've also been given side B. Well, side B would have to be one of the rays of angle A. So maybe what I do is I think of B being somewhere over here. So maybe it's somewhere there. What that would do then is that would make this my angle B. So I'm going to get rid of that for a second, but that at least allows me to say that I am going to put on an angle measurement, a side length on this ray, and I'm going to measure out that that is going to be 20 centimeters. Okay, now that I've measured out the length of B and how it has to lie on my diagram given angle A, then I know that the end of this vertex the end of this line segment must be vertex C. Well, at least that gives me then something for me to be able to construct and lie side A. So maybe I have side A, and I can say side A then is going to hang down like this. That is going to have a length of 13 centimeters. And I know then that this length would have to come all the way across and connect to form vertex B. There's me going through and constructing my triangle. Now I'm just going to get rid of that floating side A over here. Oh, but wait a second. I just noticed one key thing as I drew that diagram. I made an assumption that that side A had to lie on that angle to construct my triangle. Okay, I'm going to go backwards for a second. And really what I'm going to do is I'm going to remove any assumption of angle when I create the position of A. So what I'm going to imagine then is that my side A just hangs down. And so it's just going to hang there at a length of 13. What I could see then was that if I rotate that out, I can then put the bottom of C at the position B, and I could then construct my triangle. That makes sense. However, I could have put side A in a different position to construct that triangle. It could have been possible that rather than have A lie in the red position, I could have had A lie in the green position. That would have been my length of 13, and it instead would have said that this green position of B would have constructed my triangle. So instead of rotating my gold side A out, I could have rotated it in to construct my triangle. What that means is, given the information that I had, I could have had two different triangles. That maybe what I have is I have the red triangle. And for a lot of us, we look at that a little bit more as a normal triangle because it has the appearance of an acute triangle. Here's the position of B with a side length of 13 and a side length of 20. However, we could have had the alternate triangle, and we'll call that one the green triangle, that instead this should have been the position of B with a side length of 13 and a side length of 20. So given the fact that I was one angle and two sides, in that information, I actually could have created two different triangles that satisfy. And so, just to recap, what you'll see on the screen then is me constructing those two possible triangles, but within one diagram. Now, I want you to notice a couple key things. First off, we've got a little bit one of those puzzles. If you look at that diagram as drawn right now, I hope that you can see that we have three triangles in the diagram. However, there's only two possible triangle ABCs that fit that information. So the first thing I want to draw your attention to is we need to use some different labels. So the first one may be, I cannot have B lie in the same position at two different times. Lie in two different positions at the same time. And so I'm going to use subscript to denote that maybe I have angle B in position 1, or I have angle B in position 2. What that does then is it creates triangle ACB1 as such, and it creates triangle ACB2 as such. That I do see on my diagram triangle B2, CB1. However, that triangle cannot exist because angle B is in two different positions at the same time. What triangles are we looking for with the properties? Angle A being 30, side A being 13, side B being 20, and we notice that both of those gold diagrams satisfy those properties. So again, given that information, it was possible to have two triangles. So now let's take a look at another scenario where I gave you an angle, I've given you its corresponding side, and given you a second side. So again, one angle and two sides. For us to go through, we can create that triangle again. And so I have my 30-degree angle. I have side A being 25, which I know has to be opposite that 30 somehow. And then I've got side B being 20. So this sounds an awful lot like the previous problem, where I can extend and call this 20 centimeters, placing B opposite that side. And then I can go through and I could say that side A comes way out here. And since I had an opposite side, corresponding side from that angle, I could now connect those two and form triangle ACB. I just want to draw to your attention, in case that there was any part when given the last problem, we had an idea that said, oh, okay, so if I'm given an angle and its corresponding side, and then a second side, oh, then I could have two triangles. I just want you to imagine tackling this problem similar to the previous one, and hopefully we can see pretty quickly why there can only be one triangle in this instance. What I'm going to do is I'm just going to drop down side A as we did before. This time it's a much longer side length. It has a length of 25. Is it possible for us to then rotate that triangle out to that position of B and then form a triangle? Yes. And so we could come up with then triangle ACB just as it looks on your screen. All I'm going to do is I'm going to highlight that triangle in yellow based on the way we could swing out side A. However, when we went to take a look and see, could we swing that up the other direction, hopefully we notice that since side A is so long, that if we continued to rotate it, there would be a point where it would lie directly on top of that side and actually extend a little farther. That the only way that we could go through and actually get that bottom side to come up with the bottom of angle A would be to extend it past angle A. Yes, it could lie in this position, but as soon as we rotate that side outside of angle A ceases to exist. And because of that, we cannot construct that triangle. In fact, there is only one triangle that could be constructed given this information, and it is triangle ACB. So, just to sum up a little bit, I want to draw to your attention a couple key things. In the last problem, we were given an angle, we were given the side, and in that instance, we had two triangles. However, in this problem, we were given the angle. The only thing I changed was the length of the corresponding side. And because of that, we might be able to see an easy way for us to determine whether there are two triangles or one. Quick thing to note, that when given an angle, a corresponding side, and another side, just as what's been given in the last two problems, then it is possible to have multiple triangles. However, we saw that in one case we had two, in the other case only one. So how can we tell the two apart? Key feature: if the corresponding side, that's why I've circled A, is longer than the other given side, then we only have one triangle. You can only swing that side out wide, farther away from angle A. However, if the corresponding side is shorter than the other given side, then it's possible to have two triangles. So, hopefully a quick, easy way to kind of see that we've been making some assumptions as we've gone through to create triangles. And some ways to be able to tell that depending on the information given, how many possible triangles could we construct? Okay, so now you take a look at the three properties I've given you, and we do a very, very quick check. And we say we've been given an angle and its corresponding side, and when I compare that corresponding side, I notice it's smaller than the other given side, and therefore my instinct means two triangles. I would like us to draw our attention to something that can also arise. Me, very quickly, and this is not one where I would ask you to work through, but it's one that you can encounter. I'm going to draw all those properties on the given triangle. I have my angle of 30 degrees. Side B I can add in by extending one ray of angle A. Since it is shorter, then I know that I could swing it out always and construct that triangle. But I've made one key assumption, that that side length of 9, that side A, the corresponding side, is even long enough to reach the bottom. So for me to do a quick check, I have to make sure that I don't automatically draw the conclusion of the blue. So what I'm going to do is I'm just going to slide over a little bit, and I'm going to construct that same triangle without making the assumption. I know that the shortest distance between 2 points is a line. And the shortest distance between a point and a line, if I was to extend this bottom ray, is a line that is perpendicular. So if I wanted to see, is side A even long enough to make it to the bottom of angle A, I can construct a right triangle. And now what I'm going to do is I'm going to compare the properties in that triangle. So the first thing I can do is I can look at the two sides on that right triangle that I have labeled, and I notice, based on the 30-degree angle, I have opposite and hypotenuse. And so I know that opposite and hypotenuse would be a sine ratio. And so if I calculate the value of sine 30, I can compare that. So I'm going to compare that to the actual values that I have on that triangle, that being opposite over hypotenuse. And so if I make a calculation of sine 30, which I can calculate and know is 1/2, then when I compare that with 9/20, I notice that 9/20 is less than 1/2. And so for that triangle to even exist, my opposite side would have to be half the length, at least half the length, of my hypotenuse. And in this case, the 9 is too short. And so therefore, what I just found is there is no possible triangle with those properties. And so in that case, I can always do a quick check to see, is the triangle possible, even though at the very beginning, my instinct was there's going to be two. Now, I just want to draw to your attention a little bit that you could have gone through this a different way. That had we gone through and dealt with this as triangle ACB, very quickly you could have said that you were going to find angle B. And so then therefore that is sine 30 over 9. And you could have used your sine law again. However, when we go through to find what angle B is, then we're going to see we get an error again. And I'll draw your attention back to the very first topic we did to make sure we understand why we get an error to that. That error is telling us something's wrong with the information given, and we can now see from the second example, the second triangle that we drew, that it was not possible for us to create that triangle in the first place with the given properties. Now, before we get to the point where you're like, okay, so you're throwing all these properties at us of a triangle, what's the point? There's not even, this is all just theoretical. I want to give you a second to read the problem on the screen right now. And yes, you got to deal with my messy cursive. Meg and Chris are about to launch a weather balloon. Meg's rope is 8 meters long and makes an angle of 36 degrees with the ground. Chris's rope is 6 meters long. How far is Meg from Chris? A very practical situation. So let's go through and let's try to break down the information in the problem. First off, we should notice Meg's rope is 8 meters long, Chris's rope is 6 meters long. If that's the case, we must agree that Chris must be standing closer to the balloon because he has the shorter rope. So if I was to draw that diagram, then what I may have is Meg standing in this position and maybe my balloon up top. And there is a rope attached that is 8 meters long. While at the same time, Chris is standing over here, but it would have to be a steeper line because it's a shorter rope. And his rope is 6 meters long. We know that Meg's rope makes an angle of 36 degrees with the ground. And so, for us to go through, we could figure out how we could solve that problem. How far is Meg from Chris? Well, we can go through, and now that you have a side and its corresponding angle, you can use sine law to come up with what angle C is. Once you know what angle C is, you can use that to find what that top, let's call that a B for balloon, the angle at the balloon, which then allows you to solve for side B, which is the distance between Meg and Chris. Do you notice at the very beginning of the problem, we made a big assumption that given the information in the problem, there was nothing that spoke about how Meg and Chris stood relative to each other. That for most of us, we would have drawn a diagram that looked like that. But we need to recognize that there was a completely separate, but related, diagram that could have fit that information. I can start with the exact same assumption. Well, Meg's rope is longer than Chris's, so Meg must be standing farther away, or Chris closer to the balloon. So, Meg is coming all the way out here, and her rope is 8 meters long, but maybe Chris is standing on this side with a steeper rope, his being a shorter rope. Maybe, for instance, the wind is blowing hard in that direction, and so both Meg and Chris are standing on the same side of the rope, of the balloon. In that instance, we would now have that as our diagram. But notice we could go through and we could deal with that the same way. You could now go through and say, I can use sine law because I have a side and its corresponding angle, so therefore I find angle C. That would then allow me to determine what angle B was, and then therefore find B. So notice within the problem that it is possible for two different scenarios to occur when only given certain information. We have to be mindful of that when we create our diagrams, always. Okay, so to save us some time, I've just gone through and created these two diagrams that represent Meg and Chris. And I've labeled Chris as C1 on the one diagram, and then Chris as C2 on the other diagram to just talk about the different positions that we could be in. What I've then gone through was the beginning of both parts of the problem. We would have used sine law to go through and try to find out what angle C was. And so in both instances, I've done the trig work for you. Now what I want to get to is another issue. So up until this point, we've been trying to break down the problems that can arise when we're given certain information about a triangle. We've been spending our time drawing diagrams to try to get what was possible. No triangles, one triangle, two triangles, infinitely many triangles. Now we're going to transition a little bit into what becomes a trigonometry issue, and specifically a calculator issue. I just want you to look at all that green work. And can you please take out your calculator? You would, at the end of that green work, now take the inverse sine of 8 sine 36 degrees divided by 6, and you would calculate that and round that off to come up with your angle C. Without doing that right now, though, can you just notice one big issue? I'm calculating the exact same value for both of my triangles. Yet somehow it's supposed to give me this acute angle in triangle ABC1 and this obtuse angle in triangle ABC2. How does this and this, which are exactly the same, give me two different answers? So what we're coming into is a case that's referred to as the ambiguous case of sine law. That we can actually get to a point where using sine law will not allow us to find the property we're looking for. And it stems from a calculator issue. So on your calculator, what I'd like you to do is just really quickly punch in sine 30, of which I would hope most of us know what that is by now, and you find that you get 1/2. Your calculator is likely going to say 0.5. Now what I'd like you to do is take the inverse sine of 0.5. And you should get a little confirmation that that means 30 degrees. Perfect. Okay, now what I'd also like you to do is punch in the sine of 150 degrees. That's going to give you 1/2 or 0.5. And now let's take the inverse of 0.5 and you get, wait a second, 30 degrees. Can you see the problem? You are trying to take the inverse of a value, just as we did in green. Well, the problem is, what if my angle was supposed to be 150? We noticed that the sine of 150 is equal to 0.5. But now when I use my calculator to go backwards and take the inverse sine of 0.5, it's giving me 30 degrees, the wrong angle. Or at least, not the angle I meant. So, up in our original triangles, what if the angle I was looking for was really obtuse? My calculator is going to give me the incorrect angle. So let's take a peek for one more try. And what I'd like you to do is just to take your calculator and punch in the sine of any acute angle. So any angle that's going to be less than 90 but greater than 0. Now, you're going to get a big, ugly decimal spit across your screen, potentially. What I want you to do is burn that into your brain, or at the very least, maybe like jot down all 7 digits or 9 digits or whatever you can see. Now what I'd like you to do is calculate the sine of the supplementary angle of 180 degrees minus the angle you chose. And we should see that those two things are equal. For us to examine this calculator problem, what we need to deal with is the fact that our calculator is programmed a certain way. Your calculator has been programmed that every single time you take the inverse sine to find something, that if it can give you an answer that's an acute angle, that's the answer it gives. So you may be looking for the obtuse angle because that's what our triangle is asking for. Yet your calculator doesn't have the means to give that to you. You need to find that out. And so what I want to do is go and revisit an old diagram so we can see how we can make it functional for us. So we're going to take a look at that old triangle that we constructed way back in this video. There's the information that we had, and we came across the fact that we could have two possible triangles. So the first thing we need to notice is that if my calculator is programmed to only give out acute angles, if an acute angle is a possibility, then if I'm going to use sine law to find anything, I have to find the acute angle. And so when we examine that diagram, I would have to go through and deal with triangle ACB1 first. Because when I use sine law, sine of B over 20 equals sine 30 degrees over 13. And then I work my way through and say B is going to be the inverse sine of 20 sine 30 over 13. I know that what my calculator is going to spit out right now is an acute angle. And so I really have limited choice. I'm going to find angle B1 first. And then once I find angle B1, well, then I have the means to be able to go through and now find angle C. And once I know angle C, I could find side C. However, I just want to draw to your attention that when I do actually calculate what that is, it's approximately 50 degrees. That I know that angle B1 is 50 degrees. I do have more information on the diagram. And specifically what I want to draw your attention to is that triangle that never really existed before. Specifically, it's our isosceles triangle, B2CB1. It's isosceles because I know that both of these sides are equal. They have to be equal because they were the two sides that could have existed in different positions. And so I know that in any isosceles triangle, my base angles are equal. And so if that is 50 degrees, then that is 50 degrees. And so if I was to jump back onto my diagram, I then found 50 degrees to be angle B1. That also means that I found that that angle was 50 degrees. And therefore, using supplementary angles, I can then find my obtuse angle. So if we ever need to find the obtuse angle within that triangle, we can use supplementary angles or my 180 minus the angle that I've found. So as we've worked through today, I've thrown a ton of information at you guys. It hasn't all been new stuff. A lot of the stuff that we've talked about, the trigonometry involved, is all background knowledge. What it really comes from, though, is taking away a couple of the things that we used to deal with. Number one, the assumptions, that we don't just draw a bunch of triangles and label them differently, that we actually build the triangles as we go. The fact that our calculator has a little bit of a fault to us, or at the very least, a limitation to us. And therefore, we have to understand that limitation. Lastly, I want to give you a little bit of a bigger context situation. And when I talk about bigger context, this is us addressing something that was in last lesson. So let's take a look at the diagram I've given you. And I've given you triangle ABC with those properties. I'm going to go through pretty quickly, but we should be able to look at that and recognize that we have side angle side. And so our first action would be to find side A. And we would use cosine law with that. And if you were to go through and use cosine law, you would find that it equals approximately 7.8. Now came your next decision. And this is the one where we gave you a little guidance earlier. You have a decision to make between finding angle B or finding angle C using sine law. And our guidance to you has always been, when in doubt, find the smallest possible angle. And so you would have gone through and you should have found angle B first, because when you take a look at angle B, it has the smaller opposite side, and we know that big angles create big sides, small angles create small sides. Everybody should have been finding angle B first. We now have a context for why you should find angle B first. I'm going to go through and imagine that we did all that work. We would have then used sine law to find that angle B was about 41 degrees, and therefore angle C was 99 degrees. Now I just want you to take a look at those properties for that triangle and recognize that that diagram doesn't even really look right. That if I was to draw that diagram accurately, then there should have been an angle of 40, a side of 12, but now this side of 8 would have been shorter, so that the only way that I could find the connection would be if this angle of 99 degrees occurred. Angle A, B, and C. It makes sense that B has a relatively small angle, and C, since it was 99 degrees, had to be obtuse. However, when I draw my generic triangle that always looks acute, then I find those properties. Now, you may say, yeah, but what's the big deal? And I want to draw to your attention what would have happened if we had made a different decision. We would have found the red to be 7.8 using cosine law, but our decision now of which angle to find next, had we chosen to find C next, then we would have used sine law to find C, and my calculator would have spit out that that was 81 degrees. We now know that's wrong. But the problem was, my calculator could only ever give me an acute angle. So I don't know that it shouldn't have been 81, that it should have been 99 and not 81. We tend to just blindly trust our calculator. We then would have gone through and found the matching angle of B being 59 degrees, and we would have actually found an incorrect triangle. That's not what's given the information. So we have to be very, very careful that the reason why we always find the smallest angle first is because any triangle can only have one obtuse angle in it. Clearly, since the sum of the angles inside of a triangle have to be 180, there's no way that we could have two angles that would each be greater than 90. And so if we know that any triangle can only have one obtuse angle in it, then if we always find the smaller item first, then we'll let 180 minus the sum of the other two give us our third angle. That if we just find any generic angle first, then our calculator may mislead us by only giving us the acute angle. And therefore, 180 minus is not going to give us the correct angle for the other vertex. So again, I'm hoping that we've had a good understanding of some old information and now a little bit of an add-on to some greater context moving forward. Okay, I hope today's lesson was useful. I hope we can use it to give us a greater context with what we work with. I hope today went well. Good luck.